For more than 25 years, the International Space Station has served as the preeminent research laboratory in Earth orbit. In addition to a plethora of scientific experiments that have yielded new knowledge for use in space and on Earth, it is also a great symbol of international cooperation between 5 major space agencies and numerous other countries. And of course, as the largest space station ever constructed, it is a very inspiring example of the potential of human spaceflight, and is an excellent resource for space education in that regard, which is at least in part why we're here today. Not too long ago, I started working at a private space company building a commercial space station, and so naturally I started getting into 3D printing rockets and other spaceships. And so of course the ultimate space vehicle 3D printing challenge would be the International Space Station. So after several months of printing, when I finally had all the parts ready to go, I decided to record myself building this model so that I could talk with some detail on some of the major features of the International Space Station. Now I do want to make it clear up front that aside from one module, I did not design this 3D printed model, and all credit for translating the actual space station into a 3D printable version goes to the original authors, who you should definitely check out in Thingiverse if you want to build this, and I will include links to their pages in the description to this video. I did make some modifications though to add some color to the model, both for the purposes of illustrating certain details of the space station and also just to make it look cooler. On that note, the machine I used was a Bamboo Lab A1 with the multi-material AMS add-on. As you can see, it worked out pretty well in this regard, although it did end up wasting a fair amount of filament along the way. But in case you do want to print this yourself and you don't have multicolor capabilities, the model is still totally printable without them. There are also a few additional components that you'll need to actually assemble this thing, which I am including on screen now. And while, as I said, this model did take several months to actually get everything printed, it only took me about a week to fully assemble, which was a lot less than the time it took to research for this video to describe the station in some amount of detail. Now, one thing I want to mention before we start is that as a whole, the International Space Station is so complex that you could easily fill at least a single college course on discussing space station operations and history and individual subsystems. So instead of doing that, I won't go into great detail for every module and element of the space station, but I'll at least try to give a cursory look at each of them. And of course, if you're interested in learning more about any of these modules, there's plenty of information available to you on NASA's websites. I'll also note quickly here that I will be using some technical terminology during this video, but I will try to explain myself whenever possible. One important example of this is the determination of directions on the space station. These are the same directions as are used on ships on Earth, with the addition of zenith, which means pointing away from Earth, and nadir, which is pointing towards Earth. These directions are going to be very important for understanding where everything is located on the space station, so just make sure that you're aware of this beforehand. As more technical terms come up, I'll also include notes to explain myself. So if you'd like to build one of these stations yourself, or if you're just interested in learning some more about the International Space Station, we can get started with actually building this thing. So we'll start with the first module to be launched, the Functional Cargo Block, otherwise known as Zarya. This is the first module in the Russian orbital segment of the International Space Station, which are the modules that are primarily built and operated by Russia. This module was built in Russia and launched from a Russian rocket in 1998. However, it was provided funding from the United States, and originally provided power and propulsion to other modules on the space station. Nowadays, the solar panels have had to be retracted to make room for other elements, and while the engines have been disabled to make room for the service module, which we'll talk about later, the propellant tanks are still functional, and so they're kept for additional fuel storage. I'll also note here that I had printed these solar panels in 2 parts and then had glued them together before starting recording. And yes, I did also forget to install a panel on the side of the module. Next up, we have the first module of the United States orbital segment, which is not limited to American components, known as Node 1 or Unity. This is the first American-built module on the space station. And while it's relatively small compared to some other modules, it contains 6 common berthing mechanisms, which were used to expand the station as it was built up. These CBMs are used to connect various modules on the USOS part of the station, and in principle can be disconnected and reconnected to move station modules around as necessary. This happened a few times throughout station construction, but to keep things simple, I'm just constructing the station in its final configuration. Now in the 3D model, each of these CBMs uses a threaded rod to allow the other modules that it's attaching to be removed more easily, and also for improved structural integrity of the final assembly. Well, the axial CBMs printed all right, the radial ones didn't turn out well enough to actually put these threaded rods into, so I had to drill them out a bit and thread them using the rods themselves. Granted, a tap and die set would have been more optimal here, but I was able to make it work with what I had. The CBMs that aren't connected to any modules have a sort of pedal system that covers them to protect them from micrometeoroid impacts. Now in the model there is a separate part for this covered CBM, but once the station is fully assembled we'll be revisiting this part. Another detail we'll see on most of the modules that were launched from the Space Shuttle are these trunnion pins that were used to carry the module within the Space Shuttle cargo bay. This also allowed the shuttle to carry modules and elements that weren't perfectly cylindrical. And you will probably notice that while I was building this thing, I did manage to break a lot of these pins. Now another part you'll probably notice in a lot of pictures of this part of the station is the pressurized mating adapter number 1. This component was used to connect Zarya to the aft of node 1. Another PMA was attached to the forward end of node 1, but it was relocated later, so I didn't really need to include it here. This PMA also contains electrical conversion hardware to interface between the Russian and American electrical systems. PMA 2 and the future PMA 3 were used to dock to the Space Shuttle and are now used to dock to other visiting vehicles. For non-Russian vehicles, this is done with an international docking adapter, which converts the Russian APAS system to the NDS spec. For a few weeks after Zarya was launched, it was orbiting in space on its own until the Space Shuttle was able to bring up the Node 1. The shuttle then grabbed onto both modules and attached them together. The fact that this actually worked, with Russia developing one module and the United States developing the other, and never having actually connected the two modules on the ground before, makes this a pretty impressive feat of engineering, especially considering this was the late 90s we're talking about. Now the printed model doesn't have a place to use one of the threaded rods that are connecting between the USOS modules, but considering how much weight this joint was going to have to handle, I decided to reinforce it with its own threaded rod, which required drilling out both the PMA and Zarya. This was pretty tricky to do by hand, and the modules were then offset just a little bit because the hole wasn't perfectly centered, so I would probably say that a drill press would be the best way to do this accurately. And also, instead of using a tap, I just threaded the rod into the hole to cut out the threads. But despite the holes being misaligned slightly, it was able to connect fairly well. And with some added glue between the modules, there wasn't any problems after that. Now unfortunately, due to the symmetric design of Zarya, I did actually install it upside down here. The only way I noticed this is because one of the docking ports has a cylindrical inset to it that would have been better for the Rassvet module to connect to it more effectively. This turned out not to be a big deal because the super glue that I was using was sufficient to hold the module in place, but just for the sake of completeness, I'll mention it here. Now unfortunately, because I was working in a gravity environment, I wasn't able to construct the station in the same sequence that it was built in orbit. If you want to try to do this yourself, it's probably possible, but the fragility of some components made it easier to just build out in the sequence that I did. Also, the actual International Space Station has undergone some reconfigurations over the years that it's been in orbit. So even if we were to go in chronological order, the actual assembly process would mean that some parts would be moving around to places that they wouldn't physically connect on the 3D printed model. So with that in mind, I'm going to go out of order for these next few modules, but I'll still include the launch dates and integration timeline for them. Now the next module we'll be taking a look at here is the Destiny Laboratory, also referred to as the US Lab. The Destiny Lab has a large number of ISPR racks that can house equipment that has been flown up to the space station for operations or for running experiments, and so it primarily acts as a scientific module. The module also has a prominent window that is set up within one of the ISPRs to allow the crew to view Earth and take pictures of it from space. Now for this printed model, I did actually use a multicolor setting, but you could probably get away with just using a Sharpie for the window. There's also a small box part that mounts to the zenith side of this module that is used to connect the truss to the rest of the station, which we will be getting to shortly. Otherwise, the build process for this module is essentially the same as Unity, except that there are only 2 CBMs that you need to set up. Now before installing the US Lab to the rest of the station, I decided to construct the S0 truss and attach it to the Destiny Lab first, to make it easier to connect the truss to the rest of the station model. As a whole, the truss system routes power from the solar panels to the rest of the station modules, as well as providing radiative cooling for the station through its large radiators that are connected via coolant lines to the USOS. And so the S0 truss structure is where these connections to the rest of the station take place. We'll get into actually building those panels and radiators later though. Some of these small boxes that we see in this model are used for conditioning or distributing power that's received from the solar panels. The struts by which the truss is attached to the US Lab are not using the common berthing mechanism used for other parts of the station, and instead uses its own dedicated structure. These struts were pretty tricky to install, so I did use another US Lab that I had printed to sort of line things up to make sure they were going to fit. I attached the largest strut section first before gluing the truss itself into the Destiny Lab, and then very carefully attaching each of the individual struts. The smaller struts actually do have a sort of handedness to them, where one of them is intended for attaching to the right side based on a chamfer that part has. So if you do print these, make sure to mirror these smaller struts instead of just cloning them. This part also took quite a lot of extra material to print in multicolor, and in order to remove some supports, I had to break some of the struts that were inside the concave section of the truss. But these aren't very noticeable once you get it fully assembled, so I think it turned out pretty nicely anyways. Once the glue on the truss and the Destiny lab are fully dried, I threaded the CBMs a little bit further on both node 1 and the lab, and then attached the two modules together. In this case, make sure you have these small CBM connector pieces installed on the threaded rod first before attaching the full module. Now with Zarya, I did have to glue it to the pressurized mating adapter to properly affix it to node 1, but in this case I didn't glue these threads together so that this way I can rotate the various modules of the USOS to make sure that they're all aligned properly. The next module I built is node 2, otherwise known as Harmony. Structurally, this is quite similar to the Unity module, but this one also contains a bit of extra space that is used for crew quarters, as well as including space for other ISPRs for experiments and operations. This module was built by the French-Italian company Thales Alenia Space in Turin, Italy, which means that I'm probably not pronouncing the company's name right. Upon completion, it was handed over to the European Space Agency, who then transferred it to NASA, in return for NASA flying up a future ESA module. This ended up being the Columbus Laboratory, which we'll get to shortly. In its current configuration on the station, Node 2 connects to two other laboratories besides the Destiny lab, and has two pressurized mating adapters attached to its forward and zenith sides that are used for docking visiting vehicles. Historically, these docking modules have hosted the Space Shuttle, the Cargo and Crew Dragons, and the Boeing Starliner. Since Node 2 is located at the forward end of the space station, this is a perfect place for it to be located for docking vehicles, since a successful docking approach relies on orbital mechanics to properly rendezvous. In addition to docking visiting vehicles here, Node 2 has also hosted several visiting vehicles on its Nadir CBM. Vehicles such as the Cygnus cargo spacecraft are berthed here using the station's robotic arm. We'll get into more detail on all this later though, but the point for now is that for our construction of this module, we can have the CBM connecting pieces on all of its sides except for one where the CBM cover will be placed, which will be the module Nadir. Now if you're building this yourself, it's going to be especially important after this point to make sure that all the CBMs that are going to be using threaded rods are properly threaded before you start attaching any more modules here. Once enough modules are attached to the station, it's going to get more difficult to open up and thread the holes in the CBMs, which could risk damaging the station or any other fragile components. If you do run into any problems with getting the threaded rods to thread properly between modules, you can do what I did here and put some glue on one end of the rod so that it will be strongly affixed to at least one of the modules, allowing the other one to rotate slightly. Although it is worth keeping in mind that any smaller modules that aren't going to be using threaded rods don't necessarily need to have the holes threaded out to begin with, but this doesn't apply to most modules, so for the sake of consistency, you can just go ahead and do this for all the CBMs. The next module to be added is the Columbus Laboratory. Again, it is similar in shape to the other node modules of the ISS, as it too is built by Alenia Space in Italy for the European Space Agency. This module is ESA's largest contribution to the space station, and in addition to being manufactured in Italy, it is also operated from facilities located in Germany. In addition to 10 internal ISPR racks for housing various interior experiments, the Columbus module also has 4 platforms for exterior experiments, which can be accessed and operated by the robotic arms or EVA operations. When building this module, these platforms seem kind of precarious, but with sufficient glue, they did stick together well enough. Also regarding the printed model, this is curiously one of the few modules that has one of these grapple fixtures included with the 3D printed design. These grapple fixtures are used by the robotic arm to grab onto the station modules and move them around. Alternatively, they serve as base points for the robotic arm on which it can plant itself as it inchworms across the station. But we'll get into more detail with that later. Next up is the Japanese Experiment Module, otherwise known as Kibo, or JEM for short. This is the largest single module of the International Space Station, and contains 23 ISPRs for scientific experiments and operations of the station module. In addition to the large pressurized volume of the primary module, there's also an additional pressurized volume in the experiment logistics module mounted to its zenith. At the opposite end of the module from its CBM, there is also an exposed facility for experiments taking place in the vacuum of space. This side of the module also has an airlock through which experiments can be passed to the exterior of the station using the JEM's own robotic arm. The module was built by the Japan Aerospace Exploration Agency, or JAXA, in Tsukuba Space Center as JAXA's contribution to the space station. An interesting note about the JEM is that if you look on NASA's timeline of the ISS construction, you'll notice that the experiment logistics module, this upper part of the module, was actually built and installed to the station before the main body of the JEM. This is due to this experiment logistics module being originally berthed to the zenith side of Node 2 before the JEM module was delivered and this upper module was relocated. This exposed payload facility was also used to transfer experiments from the payload bay of the space shuttle. Up to 10 experiments could be attached to the sides of the payload facility, which can be serviced by the robotic arms or through EPA operations. Now, as far as the model goes, this tray-like component is actually used to transfer experiments from the space shuttle, but it hasn't been used since the space shuttle's retirement, so I didn't actually end up including it in my model. I also just glued in all these experiment modules to the exposed facility, but if you wanted these to be removable, you could easily install magnets on them. The exposed facility experiment modules are also a bit fragile, so if you're just gluing them in, I would recommend waiting for the glue to fully dry before you attach the exposed facility to the pressurized module. So as long as we're still working on the JEM, we can go ahead and construct the JEM Remote Manipulator System, which is the robotic arm that services the exposed facility. From inside the pressurized module, astronauts can control the remote manipulator system to operate experiments on the platform without needing to go outside and do that themselves. The arm can also assist with delivering payloads to the exterior through the JEM experiment airlock. The arm itself is comprised of both a main arm and a small fine arm that attaches to the end of the main arm, both of which have 6 joints to allow for large sweeping motions as well as fine precision motions. Now, the 3D printed model has the JEM RMS components simply glued together. However, with some difficulty, I was able to attach magnets to the joints of the printed model to produce an articulating version of the JEM RMS. This was a pretty involved process and involves getting glue on your fingers quite a lot, but if you do want to do this yourself, hopefully this video can help relieve some of this difficulty. To do this properly, you probably would want to just redesign the arm segments of the RMS, but I was able to get it to work with the original designs. We can take advantage of the sockets of the pin and socket joints on the arm segments that have them by reaming them out slightly in order to fit the small magnets inside. The extent to which this is necessary will depend on the quality of your printer. You may also need to do this on the small fine arm piece as well. And all you need to do here is to drill out the socket holes such that the small magnets will fit inside with or without glue. To assemble the arm segments, you can first insert a series of magnets into the socket joint before gluing the two halves together. This isn't necessarily the only way to do this, but it did work pretty well for me. The small fine arm magnet can be installed in a similar manner. Now, after installing the first magnet into the arm system, you'll want to take note of the polarity of the remaining magnets as you continue to install them in the arm. Individual joints can be different polarities from each other, but you'll still need to make sure that each of the two magnets that connect in a joint are properly aligned. For the 90-degree socket joint that will attach the arm to the JEM pressurized module, you may also need to ream out the socket joint to fit the magnets in, but you may also encounter an issue where the pin of this part is too small to fit within the mounting hole on the pressurized module. If this is the case, you can just put a small dab of glue on this pin and allow it to dry before installing the arm assembly. This will result in a slightly increased diameter to this pin. Now, if possible, when installing magnets to arm segments that will be attaching to existing magnetized joints, I found it kind of handy to use the whole stack of magnets to keep track of the polarity of individual magnets. I also used a marker to simply put a dot on the side of the magnet that I want to keep track of, but you could also probably just use a compass to even simplify this further. This is also around the point where you might start getting glue on your fingers if you haven't already, since it's pretty tricky to hold one of these individual magnets in place while you glue it onto one of the ends of the arm that uses a pin for the pin and socket joint. The optimal tool for this would probably be a plastic tweezers, which, now that I've looked back on this, I could have just 3D printed one at the time. Besides this option though, you can also just use your fingers and maybe a plastic item such as a pen or marker in order to apply pressure onto the magnet as you're gluing it in place. Now, as mentioned, you're going to want to make sure the polarity of the magnets matches up between the different joints, but at least for the arm segments, if you do get them backwards at one point, you may be able to just get away with using the arm in the inverse orientation. You'll only be able to use this trick once though, so just keep track of the magnet's polarity as best you can while you're actually assembling it. This will also be especially important for the 90-degree socket joint, since this component is basically essential for actually mounting the JEM arm to the pressurized module. Another potential trick you can use for the arm segments if you're having trouble is to attach the two smaller magnets to two larger magnets, or potentially just a metallic work surface, to hold them in place while you attach the arm from above. Now, of course, you could just print and glue all of these individual arm segments together for a stationary assembly, but if you manage to construct this magnetic version, it does look pretty cool and is able to support its own weight in some orientations. With that being said though, I won't install this arm with the JEM module until we get to installing the more of the detail elements to the station, just to avoid losing or breaking any of the more fragile parts. Now, going back to the station as a whole, we can install both the JEM and Columbus modules. And you'll see here that originally I did these backwards. If node 2 is facing the forward direction of the station and the truss is on the zenith side or in the up direction, then the JEM module should be on the port, which is the left side, and the Columbus should be on starboard, which is the right. Now, if you've allowed your modules to rotate sufficiently, you could just rotate node 2 around 180 degrees and then rotate the other modules to match if you did it backwards like I did. Unless you've done something different for the nadir CBM of node 2, which we will look at in the future. The main thing to note here though is that after this point, the modules are going to get more difficult to remove and relocate in the event that you attach them in the wrong locations. So just double check your space station before you attach modules in case you put them in the wrong place, which is probably just generally good advice for building a space station. While we're installing modules to node 2, we can also go ahead and install the remaining 2 pressurized mating adapters to the forward and zenith CBMs. The forward PMA was originally used as a docking point for the space shuttle, with the Zenith one acting as a backup. As previously mentioned, due to the retirement of the space shuttle, these PMAs were eventually outfitted with international docking adapter conversion kits to allow commercial crew vehicles to dock to the space station. As far as the actual 3D printed models go, they're almost identical to the PMA-1, so the assembly process is essentially the same. However, since I had some 3D printed commercial vehicles that I wanted to be able to dock to this space station model, I also installed magnets on the IDA side of these PMAs. However, I waited till after the station was assembled to actually install these magnets to make sure that I had them lined up with my commercial vehicles. If you haven't made any 3D printed vehicles yet, then it's easy enough to just take note of the arrangement of magnets on the docking adapters. But if you already have a 3D printed vehicle, which I did at the time, then it's especially important to mark which side of the magnets is actually going to attach to that, and then make sure you glue it the correct orientation into the PMA. All this could probably be made a lot more simple if you just had a compass available, which I didn't at the time of recording. We'll go into more detail on the magnets later though, once we get to the point of actually attaching vehicles to the station. The next module we're building here is the Quest Joint Airlock. This module allowed astronauts to perform spacewalks on the International Space Station using both American and Russian spacesuits. Prior to this, spacewalks had to be performed using the Russian airlock on the Zvezda module, which we haven't gotten to yet, but we will soon, or using American spacesuits from the airlock of the Space Shuttle. The Quest Joint Airlock was designed to allow both Russian Orlan spacesuits and American EMU spacesuits to be used for spacewalking from a single location, and the airlock itself can accommodate up to 2 spacewalkers at any point in time. There are 4 high-pressure gas tanks mounted on the exterior of the airlock, 2 for oxygen and 2 for nitrogen, which were installed after the module's delivery to the space station. These gas tanks are used to repressurize the airlock at the conclusion of a spacewalk, and also to repressurize the rest of the space station as necessary. Now, regarding the 3D printed model, later on we're going to be installing an external stowage platform to one side of the Quest airlock, which takes up 2 spots used by these trunnion pieces. So to avoid needing to cut these out later, you might want to not install these until we actually get to the ESP installation. Now, before installing the airlock to the rest of the station, definitely want to make sure that the top half is properly glued down to the bottom half, since you want to make sure you grab it in such a way that you avoid damaging the truss while you're threading it onto node 1. The circular piece representing the actual airlock door faces nadir, which is the downwards direction of the station. So the EVA toolbox piece will be facing forward, and the 3 tanks will be on the nadir side as well. You might also want to keep this one slightly loosely attached to begin with, since there'll be a few times where you might want to rotate it slightly to get it out of the way of attaching other modules. The next module is Node 3, otherwise known as Tranquility. Once again, this module was built by Tali Zalenia in Italy, under the direction of ESA for eventual delivery to NASA. And once again, it follows the similar design concept of the other Node modules. Node 3 connects to a variety of other important modules on the station, those being the Cupola, the Bigelow Expandable Activity Module, or BEAM, the NanoRacks Airlock, and the Permanent Multipurpose Module, all of which we will get to in due time. And as it is structurally similar to Node 2, it can house up to 8 ISPRs inside. Some of the space is taken up by an exercise module, and arguably one of the most important things on the station, a space toilet. The Zenith CBM of the module is currently unoccupied, so on the 3D printed model I included the CBM cover on this Zenith port. Also, since we're eventually going to be installing the Nanoracks airlock to the local axial forward direction of the module, you don't really need to install the threaded rod to this port. And if you do, like I did here, you'll have to remove it later. Also, make sure that the nadir port is drilled and threaded sufficiently to allow more than half of the threaded rod to fit into the module here, since the cupola that we'll be attaching to this port is rather small. For attachment to node 3, we also have the Bigelow Expandable Activity Module, or BEAM, which is printed in a single part, but you might have to drill it out to fit the threaded rod into it successfully. This inflatable space station module has quite a bit of history to it. Developed by Bigelow Aerospace, it was launched in 2016 after 2 test articles had been previously launched into space, which as of recording are still orbiting Earth. It was originally intended for a 2-year technology demonstration, but performed so well that this was extended to allow it to operate until 2028. Unfortunately, in early 2020, the company was shut down, and so there was no one left to actually support the module, and so operations were transferred to NASA. Nowadays, the beam acts as a storage compartment on the station. The last full-size module of the USOS part of the station is the Leonardo Permanent Multipurpose Module. Once again built by Thales Alenia in Italy, this is one of 3 multipurpose logistics modules that would be sent up in the Space Shuttle cargo bay for temporary attachment to the ISS to transfer cargo. Once this mission was completed, the module would be placed back into the cargo bay of the shuttle for return to Earth. Thales Alenia built 3 of these modules, named Leonardo, Raffaello, and Donatello. While these are the names of 3 Italian Renaissance men, they are also names of Teenage Mutant Ninja Turtles. And so through some copyright negotiations, NASA got a TMNT patch made for the MPLM mission. Just before the Space Shuttle program was retired, the Leonardo module was delivered to the ISS and remains there to this day, where it functions as extra storage area and also a place where astronauts can get a bit of privacy. Now to install Node 3, Beam, and the PMM, you're going to want to install them in this order to make sure that you have clearance from the truss. The CBM of Node 3 with the CBM cover should be facing zenith. And if you didn't already thread the rod on the nadir port of Node 3 for the cupola, now is probably a good time to go back and do that. Once this is done, you can install Beam on the station aft CBM of Node 3, and the PMM on the station forward CBM. If, like me, you did put a threaded rod on the station port CBM where the Bishop airlock will be installed later, it's not a huge deal as you'll still be able to access this port fairly well even once we get the truss installed. From here, we'll go pretty far back in time, back to the Russian orbital segment, for our next module, Zvezda. This module was originally built by the Soviet Union in the 1980s by the company Energia, which is still a primary provider of space equipment for Russia, and was originally intended to be the core module of the Mir-2 space station. Due to the cancellation of that program and the eventual fall of the Soviet Union, many of the elements of the space station were adapted for use on the International Space Station, the first of which, Zvezda, wasn't launched until 2000, over a decade after it was originally manufactured. And in fact, there has been a leak present in Zvezda for about 6 years now. Despite its age, the Zvezda module has still been highly important for the operation of the International Space Station, as it provides solar power and radiator capabilities for the rest of the station, as well as another space toilet, which was especially valuable during the early days of the space station construction. Zvezda also possesses propulsion systems which are used to keep the station aloft. However, this operation is also done by visiting vehicles that dock to the aft port of the Zvezda module. Zvezda also has zenith and nadir docking ports which are used to expand the Russian orbital segment of the station. Now before recording this, I did assemble the 2 halves of each solar panel together, but since the solar panels are still operational, I decided to attach them to the main body of the module using magnets so that they can be rotated. I also attached some magnets to the aft side of the module to allow for visiting vehicles to dock. Although the magnets sunk in a bit into the hole that I drilled, which made it a little difficult for these magnets to support the weight of the vehicle. So if you do add magnets to this docking port, try to get them flush with the aft face of the module. One other kind of crazy thing I found about Zvezda is that when it was launched, the Proton rocket that launched it from Baikonur Cosmodrome in Kazakhstan had a Pizza Hut logo printed on it. Apparently Pizza Hut was pretty popular in Russia at the time, and they only paid about $1 million for this. And of course they did actually deliver a pizza to the station as well. Now when installing Zvezda to the rest of the station, I realized that there are going to be additional modules that are berthing to the zenith and nadir ports, and so I decided to strengthen the connection using another threaded rod, which required drilling and threading a hole in both Zarya and Zvezda. This had probably gone a lot better if I had just modified the original 3D file to do this, or used an actual drill press, since it was really difficult to actually get the holes aligned and I ended up having to drill them out quite a bit. But with the sufficient application of super glue, it was able to stick pretty well. Unfortunately, drilling into Zarya was modules along the primary forward axis of the stations, so it could have been a lot worse. But just keep in mind that if you do need to do this for any other modules on the station, it's going to be much more difficult once the station is already constructed as far as we have it here. Also, having the solar panels attached via magnets allows them to be removed so that they don't get damaged when you're working on other parts of the station, as they are pretty big compared to some of the other modules. At this point, the station is getting pretty big and a bit unwieldy, so I switched over to the truss section of the station, starting with the S1 truss piece. This mounts immediately to the starboard of the S0 piece, and is where the TCS radiator panel assembly will attach to. This truss module also contains some electrical switching equipment for power conditioning from the solar panels, as well as a rail system for the mobile base station of the robotic arm. As with the S0 piece, I did damage some of the interior struts while removing support material here, which wasn't really helped by the multicolor operation. This did make it a little trickier to install the MBS rail component, but overall you're not going to notice this once it's fully installed. Now when you're printing out and assembling these S1 and P1 truss components, make sure to take note of their orientation in the manual for the station model. The parts are mostly symmetric though, so actual assembly between the two isn't very different. However, if you mount them to the opposite sides of the S0 truss, it will be pretty noticeable. Just for the sake of clarity, I'll also make a note here that you will need to build both the S1 and P1 trusses to complete the assembly of the station. Next we'll be building the radiator panels for the EATS system, but these won't get installed until after the S1 and P1 trusses are installed. Now because of inefficiency in onboard systems, some of the electricity generated by the solar panels is converted into waste heat. This extra heat must then be dumped overboard, otherwise the station would get too hot to be comfortable or even survivable for the astronauts inside. This is accomplished by these massive radiator panels, which, as the name implies, radiate heat away into space through radiative heat transfer. Waste heat is delivered to these panels by means of a liquid cooling system that uses ammonia as its working fluid. This external thermal system is very complex in itself, so to avoid going too far into technical details, we'll leave it at that for now. In the 3D printed model, each of these 6 radiators assemblies are identical, and yes, they are supposed to be mounted at slight angles from each other. I did find it a little easier to actually let the glue holding the panels in place to dry if you do attach the TCS panel base to the S1 and P1 trusses, so that they can be positioned with the panels facing upwards. But again, for actually installing the truss modules to the rest of the station, it's probably best to remove these TCS components once they're done drying. Also, as you can see here, the bolt that I'm using to attach the radiator panel base to the S1 and P1 struts has its head on the side of the radiator panel base. When glued in place, this means that you won't be able to get an Allen wrench on it, but this ended up not being a problem for me, as rotating the TCS panel platform was sufficient to thread the bolt into the S1 truss itself. If you really wanted to be certain, you could add the associated nut as well, but it seemed to work just threading into the printed part. Just make sure that you actually do get the threads in properly before you actually glue everything in place. You also might need quite a bit of glue as well, since these slanted surfaces don't print perfectly smoothly as well. Now before we get to actually installing the S1 and P1 trusses, I'll also show here the construction of the S3 and 4 segments, since it'll be a lot easier to install all the truss segments together one after the other. The S3 truss piece is rigidly connected to the S1 piece, whereas S4 is connected with a solar array rotary joint that allows the station solar panels to rotate a full 360 degrees without worrying about cables getting snagged due to a slip ring assembly. Now as far as actually building a 3D model of this is probably one of the more precise assembly operations involved here. The head of the bolt that passes through the sarge should be on the S4 side of the truss, allowing you to still reach the nut on the S3 side. Even so, it's pretty tricky to actually get a handle on this nut once it's fully installed, and so far I've only been able to do so using a pair of tweezers. If you glue the head of the bolt to the S4 segment though, you'll be able to rotate the solar array side of the truss itself to turn the bolt in place. And so far this has been a pretty effective way at tightening this joint. On the opposite side of the rotary joint, the S4 and P4 segments contain a power accumulator assembly of batteries, which store power from the solar panels when the station orbits into the night side of Earth, which takes place approximately every 90 minutes. Now because this rotary joint only provides an interface for electrical systems, there's no way for waste heat from these batteries to be transferred to the primary TCS panels on the radiator assembly. So each of these power accumulator assemblies has its own radiator panel that is mounted to the S4 or P4 truss element. You'll also have to pay special attention to these angled pieces that contain the bolt holes for mounting 2 solar panels. If, like me, you've printed out both the S4 and P4 segments at the same time, then just make sure not to get them switched from one segment to the other. Here it's not as big of a deal if you do get them backwards, but once we install the S6 and P6 segments, you'll definitely want to make sure you have them matched up correctly. Now, it took me a while to figure this out, but apparently the reason that this is called the S3 and 4 truss pieces, and likewise the P3 and P4 trusses are named as they are, is because this truss was originally designed for Space Station Freedom, which was the predecessor to the International Space Station that was designed by NASA. In this original space station design, the truss had 2 additional modules on which rocket engines would be mounted. But since this functionality was taken over by Zvezda, these truss components were not needed in the final design. So instead of redesigning the whole truss to accommodate this, they just chopped out these S2 and P2 segments. Once again, as when we were assembling the TCS panels, it's a lot easier to get this radiator panel to attach properly if you position the S4 and P4 segments such that the radiator panel is facing directly upwards. You will want to make sure that this radiator panel direction is correct, as it does need to align with the rest of the solar panels, but again, this isn't a huge deal until we get to the S6 and P6 segments. Alright, now to go about actually installing the truss. This is a more involved process compared to the modules of the station so far, but at least now you'll have the benefit of knowing how it worked for me. Also, something I just realized while editing is that I said starboard truss for this whole first segment, where I'm actually installing the port side first. Technically, you could do this in reverse order and start with starboard, but just to avoid confusion, just take note of this. Because the truss is going to be holding up a fair amount of weight with the solar panels on both ends of the station, and because the solar panels can rotate, giving different load patterns, I decided to reinforce the station truss with 2 metal rods. This will give the station more rigidity and also will allow the mobile base station to actually slide along the truss. The exact material I used for this was an 1/8 inch diameter cold rolled steel rod of 4 feet long. I think a softer metal would probably work for structural purposes, but you'll need something ferromagnetic for the mobile base station to slide along magnetically. I first lined up the 2 starboard truss segments to see how much rod was necessary on that end, which was approximately 7 1/4 inches. This was added to the approximately 5 inches of the S0 truss and an equal 7 1/4 inches for the port truss, making the requirement for the rod approximately 20 inches long. Now there are some caveats to this which we will get to when we get to the point of actually installing the rods. But to start with, I used a bolt cutter to cut these 2 rods into 20-inch pieces. I'll also make a note here that if you did want to reinforce the S5 and S6 sections of the truss and the equivalent port segments, you would need about 6 inches for each side of the station. Unfortunately, this was about 6 inches more than I had left on the 4-foot rod that I started with, so if you were to get like a 5-inch rod or so, then this would probably give you enough material to work with. Although once it was fully assembled, the 5 and 6 segments of the truss didn't seem like they really needed the additional support. Now to actually go about installing the S1 segment, I positioned the station on its side such that the starboard side was facing up. This means that the JEM module will be facing upwards as well. The Columbus module fits nicely inside the center of a 3D printer filament spool, so I used that to support the station while I had it oriented this way. This is where you'll want to make sure to remove the TCS panels from the S1 truss segment before you attach it here. This way the S1 truss can just sit vertically on top of the S0 until the glue dries. One other thing to note here is that if you didn't already do this, this would be a good time to actually apply glue to the bolt head of the sarge joint on the S4 segment. If you really wanted to, I suppose you could wait to install the S4 segment until the S3 is fully installed with the rest of the truss, but as we'll see in a moment, there is a good reason to have this one installed beforehand. Now before actually installing the S3 and 4 truss segments, make sure that the S1 is at least somewhat dry first. The radiator panel in the S4 segment does necessitate some balancing act here, but the sarge also allows you to position the radiator panel in a direction that allows it to balance better. As you're initially placing the S3 and 4 on S1, just kind of feel out which direction the truss is leaning in and then rotate the radiator panel to balance that out. And when positioned correctly, the S3 and 4 should be able to balance on top of S1. Once the glue is dried between all these truss segments, I applied a piece of tape at the interface points to further restrict the lateral motion of the truss pieces. If you do this, just make sure you remember to remove these pieces of tape before gluing the rods on place. Again, after waiting for the glue to dry a bit, you can rotate the station back down and rest the S4 segment down on another object so that it's still supported while the station is in its nominal orientation. If the truss falls apart at this point, you'll need to repeat the past few steps. Okay, now that the port side is installed, we can go to the actual starboard side. Before gluing anything in place, make sure that the rod still fits with your truss segments, and take note if the rod is bent like the one that I have here. Now the 2 rods will be installed on the zenith and nadir sides of the MBS rail and the printed parts. I wasn't really able to capture this very well with this camera angle, but if you look at the station from a forward direction, you'll be able to see what I'm talking about. The nadir rod fits a bit more to the forward side of the MBS printed part, whereas the zenith rod fits a bit more on the actual zenith of the printed MBS system. This might be in part though due to the bend in the nadir rod. Keep in mind though that the MBS itself is sized to fit on the 3D printed rail system, so if you do have both of the rods spaced out too far, you'll have to get creative with actually getting the MBS to fit. Now to install the nadir rod, what I did was to first position it along the rail system, align it at the furthest end of the P3 truss, and then taping it in place before actually applying glue. This way you can double check to make sure that the starboard side will fit with the length of rod that you have cut. Once you've confirmed that the rod is properly sized, you can begin applying glue to various contact points where the rod makes contact with the truss. If the rod isn't perfectly straight, you probably won't be able to do this along the full length of the rod, but just make sure that you distribute the glue along as much of the length of the rod as possible. I would start from the port side and begin applying glue as I go along towards the starboard side, and applying additional pieces of tape as necessary to make sure that the rod is still held in place. It will probably take longer for the glue to dry to sufficiently hold the rod in this configuration, so you'll probably want to keep the tape on the rod while you continue the installation process. This part will probably require some trial and error, as the actual points at which the glue is starting to stick and the points at which the tape can properly hold the rod in place are probably going to vary, depending on your actual 3D printed parts and any bend in the rod. Also, if you still have any tape on the rod from earlier when you were first installing the port side of the truss, make sure that you lift that out of the way before actually installing the truss, otherwise you might get the tape stuck on the module. Once the glue has dried sufficiently for the rod to be held in place, you can start installing the actual starboard truss elements. You can start by applying glue to the port side of the S0 truss element, and then using tape to hold the S1 segment in place such that the glue will hold it on once the glue dries. Once you get it held on this way, you can apply another piece of tape at the interface section, and then apply additional glue to the length of the rod as we did with the port side. You can then do the same process for the S3 segment. Just note that since it's a bit smaller, you might need to apply a bit more glue to get it to hold in place here. If you're having trouble getting the S3 segment to hold in place, you could support it with an additional object underneath, but after some trial and error, I was eventually able to get it to stick without needing to do this. Again, keep in mind that you probably won't be able to apply glue along the entire length of the rod, and instead make sure that you can get as much coverage as possible. Also, don't worry if you cut the rod a little too short to fully extend to the far end of S3, as we'll see again in a moment that there is potential interference with this. Now technically you could do this in the same way as I did with the port side, but you'd have to be essentially holding the station such that the truss is held vertically, and I wasn't able to do that while still capturing it on camera with this workbench. The technique that I used did seem to work, however, and I did manage to get it installed. Now once the glue on the nadir rod has dried fully, the truss should be in a pretty rigid state at this point. But for the increased factor of safety, and again for the MBS rail system, I decided to install the zenith rod as well. To do this, you can start by lifting up the tape on the zenith side of the truss, positioning the zenith rod in place, and then affixing it using these same pieces of tape. Once this is done, you can go in and apply glue just like we did for the nadir rod. This one should be a lot faster and easier since the truss is already in place and you're just gluing something onto it directly. Again, depending on how much the rod is bent, you might need to fit this one on the zenith side of the MBS rail system, but it should still fit pretty solidly in this position if you can't get it to sit directly on the forward face. Once the glue on the zenith rod is dry, you can begin removing the tape from the truss. You can see here that I've got it sitting on top of two 3D printer filament spools, which is just about high enough to lift the station off of the workbench, which will come in handy in just a moment. And assuming nothing has fallen apart by this point, the primary truss structure is now complete. Here you can get a little better view of what I was talking about with the actual positioning of the rods relative to the 3D printed MBS structure. Even if they're not perfectly spaced out across the whole station, this will still provide some additional strength to support the solar panels on either end. We can now install the TCS panels to the S1 and P1 truss elements. If you've applied enough glue to the bolts and/or threaded into the small segment at the back of the TCS panel, then you should just be able to rotate the whole TCS assembly into the bolt hole on the S1 and P1 truss elements, and it should thread in just fine without needing to add a nut. Keep in mind that these TCS panels are supposed to rotate on the International Space Station, so you don't need to over-tighten them here. Now, if you do want to wait to install these panels until you've gotten more of the station assembled, that would make it easier if you have to remove any part of the Russian orbital segment, as especially once the Nauka module is installed, these TCS panels might start getting in the way if you do need to unscrew any of the connected modules. Now, before we move on to the next truss elements, there's a potential interference I want to point out here first. If either end of either rod extends out past the 3D printed struts on either the P3 or S3 truss elements, they may interfere with the rotation of the P4 or S4 truss elements, where the rotation of these small struts might be blocked by the rods. In this case, this was after already assembling everything, and it was easier to just break off these small struts than to go back and redo everything. One last thing we can do here with the P4 and S4 trusses is to install these bolts that will be used to connect the solar panels to these assemblies. In order to attach S6 and P6 to S4 and P4 respectively, we'll need the S5 and P5 segments. These segments were included on the station because the 3-4 assemblies were already taking up most of the space within the Space Shuttle cargo bay, and they weren't able to fit the full assembly in on one go. So we'll get onto those next. Now technically, the larger of the two major components of the S5 and P5 truss segments is mirrored between the two elements. Functionally, this doesn't make a lot of difference if you do just print the same piece twice and use it for both truss segments, but the only difference will be that you'll have this extended triangular section that will be pointing in the wrong direction on the final assembly. It's a pretty minor detail, but just something I want to point out. You might also have a little bit better luck if you wait to try installing the trunnions until after the glue has set between the two primary components first. This will also be the case for the rest of the truss elements as well as the external payload carriers, which we'll get to later. Now functionally, the S5 and P5 trusses essentially act as extenders to connect the S6 and P6 sections to the end of the S4 and P4 trusses. This is in part due to the design of the solar panel connection points, but also because the S4 and P4 trusses took up just about all the space within the Space Shuttle cargo bay, so these extenders were needed to actually implement the full design of the truss. Now in the final station configuration, the radiator panels attached to the S4 and P4 segments will be pointed downwards in the nadir direction. With this in mind, the S5 and P5 truss sections are oriented such that the triangular portion points in the forward direction, when the section 4 trusses are in the orientation with the radiators pointed nadir. This will ensure that you are able to fit the solar panels into these attachment points at the ends of the section 4 truss elements. The last two parts of the connected truss structure are the S6 and P6 segments. Technically, there is one other truss element to be done after this, but we'll get to that soon enough. The P6 truss element was actually the second part of the truss to be attached to the space station. It was originally pointed upwards in the zenith direction and was attached to the Z1 truss, the first truss element to be attached and the last one that we haven't got to yet. You can really tell we're not doing this in chronological order at this point. This was done to ensure sufficient power was available for upcoming expansions to the space station in its early days. The radiator panel on P6 also provided heat rejection capabilities to the early space station in a similar manner. In the current configuration though, as the thermal loops are not able to connect between P5 and P4, this thermal system services the solar power accumulator system, which is also mounted on P6. Now you'll want to take special note when building this, the direction of the two solar panel attachment points at the end of P6 and S6. These two truss elements are effectively mirror images of each other. However, the orientation of these brackets to which the solar panels attach should match up between P6 and P4 and between S6 and S4. If you look closely at the model that I made, you'll see that I actually installed these backwards, with S6 on the port side and P6 on the starboard side. The result is that the solar panels will appear offset and not entirely in the same plane as each other. This will make more sense when we actually get to installing the solar panels though. As with the S4 and P4 radiators as well, it's also a bit easier to install these on the S6 and P6 segments if you wait for them to dry a bit first before attaching them to the base plate with the radiators pointing upwards. Due to the trunnions, you'll need to set S6 and P6 on another object while you're waiting for these to dry. Once again, when installing these Section 6 truss elements, make sure that you have the solar panel brackets aligned properly before actually attaching them. To be clear, this is not what I did in the video, so you can learn from my mistakes from here. With that said, when you actually go to glue the truss elements on, the S6 and P6 elements will sit up a little higher than the S4 and P4 segments. So you'll want another object underneath the S6 and P6 segments to hold them in place while the glue dries. I would also recommend waiting for the glue to fully dry on one end before going over to the other. I'll also mention again that I was able to fully assemble the station without adding a support rod to this P4 through P6 and S4 through S6 segments. But if you would like to do so just to be sure, you can follow a similar process to what I did for the support rod in the primary truss structure. Although if you do this, you'll need closer to about 4 foot 6 inches of metal rod. Now there's one truss element left for us to build. However, this one doesn't actually connect to the primary truss structure and instead connects to a CBM on the top of the Unity node. This truss element, the Z1, was the first of the truss elements to be installed on the station, and as previously mentioned, was previously host to the P6 truss element. This module has some unique design elements to it, one of which is the manual berthing mechanism it has on its forward side. This mechanism will accept a passive common berthing module, but unlike the CBM, this attachment must be performed manually. And historically, this was only done once to house the PMA-2 temporarily during station construction. Nowadays, this MBM is blocked by the S0 truss element. Another interesting design element of Z1 is that there is in fact a small pressurized volume inside the CBM attachment point. It's not really big enough to consider it its own module, but there's a little bit of extra storage space they get out of it. As far as onboard equipment, the Z1 holds the control moment gyroscopes, or CMGs, that the station can use to adjust its angular position without having to rely on rocket engines. Essentially, these are effectively flywheels that are mounted to a gimbal mechanism that allows them to rotate about different axes. It's kind of hard to point to something similar to explain this in non-engineer speak, but one possible example could be that if you've ever used a hand drill to screw a bolt into an object that you're holding in your other hand, as the bolt is tightening and once it reaches its full threading, you can feel both the hand drill and the object in your other hand twisting in opposite directions. It's not a perfect example, but hopefully this gives a little bit of an idea of what a control moment gyroscope does. In addition to CMGs, the Z1 truss also houses communication equipment, hence the two antennas on the zenith side, as well as plasma contactor equipment, which are used to neutralize the static charge developed on the space station as it travels through Earth's plasma field. This one in particular gets really far into electrical engineering and astrophysics, at least one of which is not really my specialty. Going back to the printed model, this is one of the more fragile elements of the space station, although I will note that the antennas held together surprisingly well when they were glued in place. With that said, you'll eventually probably want to remove the Z1 truss when we're doing some other installation operations on the station, but you can test and make sure that it actually attaches to the Node 1 CBM as well. And assuming you've assembled it correctly, it's not terribly difficult to remove and reinstall. The second to last USOS module we'll install is the Cupola. Now I will quickly note here that I'm pretty sure the Bamboo Lab would be more than capable of actually printing this thing with 3 different colors, but since I already had one printed with 2 colors and to avoid wasting excessive filament, I just decided to use a Sharpie at this point. On the space station, the cupola acts as a sort of observation dome to allow crew members to look out at Earth and observe space station operations in the exterior. This is also where the control panel for the Canadarm robotic arm system is located, so that at least as long as the arm is on the nadir of the station, the operator can have visual confirmation of the robotic arm's activities. The cupola itself is quite small compared to some of the other modules, but compared to the other windows on the station, it provides a greatly expanded view of the exterior. Each of the 7 windows on the cupola has a shutter that can be closed manually from the inside. The windows are also 4 panes thick, and individual panes can be replaced on orbit, either from the inside or the outside. The cupola was originally designed by NASA and manufacturing began in the United States, but its progress was significantly impeded by heavy budget cuts. Eventually, the responsibility for completing development and manufacturing the cupola was transferred over to ESA. The primary structure of the cupola was manufactured in Germany, and the design and assembly processes were completed by Teles Alenia in Italy. Once it was finished, it was shipped back over to NASA, who launched it up on the space shuttle along with Node 3 Tranquility. A big argument when Cupola's budget was getting cut was that it wasn't very essential to space station operations. While you could say this is somewhat accurate since the station has been operating pretty effectively without it, the cupola has enabled a large number of amazing photographs to be taken of Earth from the space station. And in addition to scientific value, this also goes a long way for scientific outreach and space education, which it could be argued are a pretty good return on investment for the original cost of the cupola. Now, in order to install the cupola on the nadir CBM of Node 3 Tranquility, you'll probably want to flip the station over such that nadir is facing up. To avoid damaging it, this is the point where I would recommend removing the Z1 truss temporarily. You can then use pliers to thread the cupola onto one of the 5mm bolts on the nadir CBM. I suppose if you wanted to, you could install the cupola to the station before installing the window shutters, but at this stage of the project, we're already going to be working more on the nadir side of the station, so you're probably going to need to have it upside down anyways. The Mini Research Module 1, also known as Rassvet, its Russian name, is a small module that is attached to the nadir of Zarya and provides some additional storage space along with preserving the nadir docking port. The launch of this module was also used to send up some equipment for the future Nauka module, as well as some EVA equipment and an expansion to the European robotic arm. It was originally built by the Energia company in Russia and was flown over to the United States for outfitting by NASA and delivery to the space station via the space shuttle. This 3D printed model contains quite a few small parts, and so it's a bit tricky to assemble and also is fairly fragile once you do get it together, which is partially why I decided to wait until after flipping the station over to install this on the nadir side. Now I will note here that the cylindrical part that attaches to Rassvet is actually an experiment airlock module that was eventually attached to the Nauka module. I was unaware of this while assembling this model, and so I kept this airlock module on both Rassvet and then also have one on Nauka. So if you're looking to build the station in its most up-to-date configuration, you don't need to include the experiment airlock when you're building Rassvet. This is also the case for the radiator panel that attaches to the exterior of Rassvet, which we'll get to in more detail when building Nauka. I also didn't build a European robotic arm for the station, so I didn't actually end up using the extension that was included with Rassvet's manifest. To give a brief description though, since the Canadarm can only attach to the grapple fixtures on the USOS side of the station, its ability to operate on the Russian side is a bit limited. So the European robotic arm was developed to operate on the Ross section of the station, and uses a different set of grapple fixtures that themselves use a different standard from the USOS. Due to massive schedule delays, this spare joint that was launched with Rassvet was actually launched before the actual European arm itself, which was included on the launch of Nauka. Now this is an important detail and a good example of why you should wait till the end of the video before going and building this yourself. When I originally installed Zarya to Node 1, I installed it upside down. Now while most of the station is mirror symmetric about this axis, the Zenith port was welded over with a cap, and the Nadir port is where Rassvet actually connects to. And for better or worse, the 3D printed model does capture this discrepancy. So if, like me, you install Zarya upside down, you won't be able to easily attach Rassvet into the Nadir docking port. And since I didn't want to risk damaging the station by trying to remove Zarya at this point, I decided to carefully drill a hole into both the Zarya Nadir docking port and the Rassvet Zenith docking port in order to thread in another threaded rod. This is definitely not an optimal way to do this, so make sure to plan ahead when you're building your own space station. In any case, once you do get around to attaching Rassvet, the side on which the radiator and airlock are mounted should be facing port. Or if you didn't include these, the triangle trusses should also be extending towards the port side of the station. The Nadir port of Rassvet can also be identified as the one to which the triangle trusses are most closely located. While we're here, you can also install a magnet at the Nadir docking port of Rassvet, but make sure that you have this properly aligned with any visiting vehicles you might want to add later. Again, if you haven't actually built any visiting vehicles yet, this isn't really much of a problem, but just if you have, make sure that the polarity of the magnets is aligned correctly. The last full-size module we have to build for the station is Nauka, formerly known as the Multipurpose Laboratory Module. While it is one of the most recent additions to the station, it is technically one of the oldest modules. As you might have noticed, it is very similar in shape to Zarya and is also based on the functional cargo block base design. And in fact, this module was originally constructed in the 1990s as a backup for Zarya. After Zarya was completed, this module was eventually converted into its own science module. And while it was originally planned for launch in 2007, there were numerous delays that eventually resulted in it not getting launched to the station until 2021. Now this module does include the experiment airlock that was launched on Rassvet, which we talked about previously, but when Nauka launched it also carried up the European robotic arm, which also launched much later than it was intended to and is also not included in this model. Now I did get my details mixed up regarding the external radiator of Nauka. There is a radiator on the exterior of the module that was successfully deployed, and the one from Rassvet was included as a backup. This backup radiator, once it was transferred to Nauka, was damaged on orbit and began leaking coolant out into space. At time of recording, it appears that this damage has not yet been repaired. This made me think that Nauka had not deployed any radiators, so I did not include the actually deployed one on my model. I also printed out and glued together the two halves of the solar panels prior to recording this video. I did include magnets on the solar panels though, so that they can be actuated to point in a sun-facing direction. Attached to the Nadir docking port of Nauka is the Prichal module. This node provides additional docking ports that were originally intended to house additional space station modules. However, since Prichal needed to dock to the Nadir of Nauka, it was also delayed until late 2021. And by that time, plans for additional Russian modules for the International Space Station were adapted into plans for Russia to build its own space station. As a result, as of time of recording, only the Nadir port of Prichal is still used for docking spacecraft. This module prints as a single part in the 3D printed model, but I did decide to drill out the Nadir port to add in a magnet to allow a Soyuz vehicle to dock here. The module itself, along with the Soyuz, are pretty lightweight still, and gluing Prichal to Nauka was sufficient to support all of this weight, as long as you don't bump it hard enough for the magnets to detach. As we go to install Nauka and Prichal together to the space station, note that I have rotated the assembly such that the aft of the station is now at the top of the screen. To ensure that Nauka gets lined up properly, you'll want to have another object balancing Zvezda to make sure that its Nadir docking port is facing directly upwards. When you do bring Nauka into install, remember to keep the experiment airlock facing forwards. This is also the direction that the deployed radiator would be facing if I had actually installed it. Now, despite having an inset in Zvezda's nadir docking port, I did have trouble getting Nauka to actually stay in place sufficiently with just glue. So once again, I drilled into both docking ports to add in support for a threaded rod. As you might have noticed by now, this is pretty difficult to do accurately and to actually get the threaded rod into the center of the docking port. So if you're going to do something like this, I would recommend doing it before installing the modules together, or using more precise methods such as starting with a smaller pilot hole or just using a drill press. On the plus side though, we could say that the additional difficulty with docking Nauka to the International Space Station is at least somewhat historically accurate. On its way up to the space station, Nauka was having some propulsion issues, but these were able to be corrected before it actually got to the docking position. The automated docking procedure was able to proceed successfully, and Nauka was docked to the space station without issue. Shortly after this, though, the thrusters on Nauka fired again without being commanded to do so. This resulted in the station beginning to rotate. The station CMGs attempted to balance out this rotation, but were unable to do so. When this failed, an attempt was made to use the thrusters on Zvezda to counteract these thrusters on Nauka. However, this also proved unsuccessful. Station operators on the ground and in orbit attempted to get the station under control for the next 45 minutes, during which time the station rotated about 45 degrees out of alignment. Eventually, the thrusters on Nauka burned through all of their remaining propellant, and the station was able to be reset to its intended attitude using the thrusters on both Zvezda and a docked Progress vehicle. The station never rotated quickly enough for a crew inside the station to be in danger or even feel that it was moving this way, but this was still a rare instance of a station emergency being declared. This incident also resulted in a delay to the second flight test of the Boeing Starliner. Fortunately, there was no permanent damage and no one was hurt, and the model we're building now sidesteps this issue completely by not including any functional rocket engines. The final module we have to build for the Russian orbital segment of the station is Poisk. The Mini Research Module 2, as it's formally known, serves as both an airlock for use with Orlan spacesuits and a docking port for visiting Soyuz vehicles. This module is also very similar to the Pirs module, which was previously mounted to the nadir port of Zvezda before it was removed to make room for Nauka. The printed version of this module comes in a single piece, with the addition of a Strela arm attached to it. Unlike other robotic systems, this is a manually operated telescoping boom system, and allows cosmonauts to traverse the full length of the Russian orbital segment. You may also notice that Poisk and Pirs have a relatively similar design to the Progress vehicles. And in fact, both of these mini research modules, as well as Prichal, were launched on modified Progress vehicles that essentially had their top half chopped off and replaced with the module that it was delivering to the station. Now to install this second to last module of the station, we can flip it back over such that the zenith side is facing upwards again. After doing so, you can also go ahead and reinstall the Z1 truss. At this point, because Nauka and Prichal extend further below the truss than the US OS, you'll have to set the truss up higher in order to get the station to sit level with your work surface. Fortunately, Poisk is pretty easy to install in Zvezda since we have the inset on the Zenith docking port. And if you aren't able to position the station completely level, assembling this model in the presence of gravity should result in Poisk being mostly aligned with the docking adapter. The Strela arm attached to Poisk should also be located on the port side and facing towards the nadir. Once this is done, you can also install a magnet on the Zenith docking port of Poisk. Again, make sure you get the polarity of the magnet aligned correctly with any visiting vehicles you might want to dock here. So at this point, we have completed the core assembly of the International Space Station. All that's left are some smaller detail parts, as well as the very large solar panels. So at this point, in order to facilitate access to the entire station, I mounted it onto a green screen lamp tripod using a camera clamp, and then moved this over to the table next to my workbench. The Destiny module works pretty well as a point to clamp onto, but based on my experience, you'll probably also want to put another clamp and tripod on the Zvezda module as well to give it some additional support. And so with the station set up and out of the way of the workbench, we can get to work on building these solar panels. Now, the original 3D printed model design called for using pieces of gold foil in place of the solar arrays. I'm sure this would work well enough and probably would take less time for printing overall, but I also wanted to include the slight blue coloration of the panels as well as the layout of the individual cells. Unfortunately, my printer wasn't big enough to print these all in one piece, so I experimented with printing them in halves and thirds. Overall, I didn't really have any problems printing them in halves, and if your printer is big enough for ease of assembly, I would probably recommend using that option. Another thing to watch out for when you're printing these solar panel assemblies is that if the trusses experience any peeling off the print bed at the ends of the struts that hold either end of the solar panels, this may result in the slight gap in the strut being closed and thus being unable to hold the solar panel from that end. I encountered this issue quite a few times, and the best issue for me seemed to be to just cut a small piece of the solar panel away while leaving as much material behind as will successfully fit into the slot on the strut. Also, while the panels I printed are long enough to fit between these struts, they are only just barely so. So when you're printing this, you might want to scale by maybe 101 or 102% in the longitudinal direction. And in my experience, I found that a small amount of glue helps hold the solar panels in place pretty well. The most effective way I found to install these solar panels was to first tape the two truss segments together in the center. Start by wrapping a piece of tape around one end of one of the truss segments, then you can apply some glue to the face of the truss at which the other segment will meet. You can then wrap the tape around the intersection and allow the glue to dry. Then use a piece of packing tape to combine both halves or all 3/3 of the solar panel, while making sure not to tape either end of the solar panels. Then insert one end of the solar panel into one of the truss strut slots. Temporarily affix it in place using a piece of tape, and then apply a small bit of glue to the side opposite the tape. You can also try applying some glue to the strut before inserting the solar panel. Once this glue is applied, you can put another piece of tape over that same side of the solar panel, which should be enough to keep it in place while you're assembling the rest of the solar wing. This does get to be a rather laborious process, but since you'll be building 8 of these solar array wings, you'll get pretty good at it by the time you're done. Also, based on my video evidence, each of these solar array wings took about 10 minutes to assemble. Also, just to clarify, when I say solar array wing, I'm referring to one of these solar panel assemblies with 2 panels each. Once you have the wing assembly completed, I would recommend giving it a little bit of time to dry before you start handling it. In the meantime, you can prepare a beta gimbal assembly part to install to one end of the truss. Now maybe it's just the way I was printing these, but I had a lot of trouble getting these small bolts to thread into these holes in the center of the BGA parts. Again, a tap and die would probably have been the best way to do this, but I did eventually manage to get these holes to be widened out and then threaded in by essentially reaming them out rather than using an actual drill bit, which again would have been the optimal way to do this. Be very careful when you do this though, since if the threads get stripped after you've installed the BGA part to the solar array wing, it will be difficult to remove without actually damaging this and needing to build a whole new solar array wing assembly, which I did have to do once. Once you do get the bolt hole prepared, you can glue the BGA onto either end of the truss. In my model, I arranged these such that the slight protrusion is pointing towards the same direction as the side of the panels with the solar cells on them, but as far as I can tell, I believe these cylindrical components don't actually rotate with the solar panels themselves on the actual International Space Station. So technically it doesn't really make much difference here, but I like to keep things consistent. So once you've built 8 of these solar array wings, we can get to work on the most time-intensive installation process for the whole station. As you'll see throughout this video, the tripod I was using has a ball and socket joint that allows it to rotate, which was kind of an inconvenience at times, but also came in handy a few times to get at the station from different angles. I would first recommend starting with the solar arrays on the P6 and S6, since these are the easiest ones to get a driver on, and if you want to get a drill on them, they're more easy to access in this way. Once you get panels installed on one side of the station, immediately switch over to the other side and install the panels that are on the opposite end. This will allow you to balance out the station immediately, and also give you an opportunity to adjust these wings' positions as necessary to further improve balance. Once you get around to installing the P4 and S4 solar wings, due to the truss structure of the P5 and S5 segments, it's going to be more difficult to get a drill bit on the small bolt head. I would recommend using either a shaft extension or, if you have one, a flex shaft to allow you to hold the drill at a more convenient location, while also avoiding damage to the solar wings. The P4 and S4 bolts are a bit easier to access when you're just using a plain Allen wrench, but of course this will take longer. With these awkward angles, you definitely also want to be careful to avoid stripping the screws out on the BGA components. Now towards the end of this clip, you'll notice that I did have a lot of trouble installing one of the solar panels onto the S4 truss. If you do happen to strip out the threads on a BGA part of one of the solar array wings, you can either attempt to build another solar array wing, which is what I ended up doing here, or you may also be able to install the wing to the truss using an M3 bolt instead of an M2. I wouldn't go any larger than this though to avoid damaging the S4 truss. This will of course require drilling out the BGA to a larger diameter, as well as the solar panel mounting struts on each of the truss segments where you perform this operation. It's around this point that you can get a pretty good idea of just how big these solar panels are compared to the rest of the station. Each panel is approximately 35 meters long and 12 meters wide. Each of the 2 individual panels on each wing is actually a flexible photovoltaic blanket that folds up like an accordion, which is how they were originally stowed in the Space Shuttle cargo bay before they were actually deployed. When fully deployed, all of the wings together comprise an area more than half that of a football field. Now, this is NASA talking here, so I don't know specifically if this is an American football field or a actual football field, but the point still stands that they are quite large. All 8 wings together can produce about 240 kilowatts of power when they are all facing the sun directly. But in actual operation, the realistic range is between 84 and 120 kilowatts. Now, the example NASA uses is that this is enough electricity to power more than 40 homes. But if, like me, you find that number hard to visualize, you could also say that this is about enough power to run 100 high-end gaming PCs running full tilt on 1,000-watt power supplies. Now, there are actually several reasons why the solar arrays don't output maximum amount of power at all times. For one, half the time the ISS is orbiting the Earth, it's nighttime. Whenever the ISS orbits around to the night side of Earth, it is shadowed and the solar panels are not able to provide power, which is why the power accumulators in the 6 and 4 sections of the truss are included to provide power during nighttime. Keep in mind though that due to the ISS velocity, nighttime and daytime only last about 45 minutes each. In addition to the limited daylight available though, the arrangement of the solar arrays also affects the amount of drag that the station will experience due to the small bit of atmosphere that it is still orbiting through. More specifically, when the solar panels are arranged such that they are perpendicular to the forward direction of ISS, the surface area that is facing forward is maximized, and so they will be impacting the highest amount of air particles. Now granted, there's not very much air up there, but there are still some particles of atomic oxygen. And over time this can lead to a significant difference in the amount of propellant required to keep the station aloft over a certain number of orbits. There's also a challenge of thermal distribution across the solar wings. Depending on the orientation of the solar panels, certain areas might be receiving more sunlight than others, leading to them absorbing more heat and then being raised to higher temperatures. If there are certain parts of a truss that are at higher temperatures than others, this can cause stress in the material due to this thermal disequilibrium, which could potentially impact the structural integrity of the solar panel trusses. So this is another factor that needs to be taken into account when orienting the solar panels. In spite of all this, the solar arrays are still capable of providing a surplus of power to the space station, so running out of electricity usually isn't an issue. However, these solar panels are getting pretty old, and since they have such a large surface area, they are also prone to damage from micrometeorites or orbital debris. The atomic oxygen in the upper atmosphere also contributes to the degradation of these solar arrays, which were originally designed for a 15-year lifespan. So, to ensure that the station continues to have enough power, NASA has been installing rollout solar arrays, or ROSAs, on top of the existing solar array wings. These newer solar panels use more recent technology and are more effective than the larger solar array wings. At time of recording, all but 2 of them have been installed over the previous solar panels. However, I had enough trouble mounting the solar array wings to the station in the first place, so I decided to just leave it as it is without installing the ROSAs. Now at this point, I finally got around to installing the final module of the space station. If you're going to build this yourself, you could definitely do this a lot earlier than I did. I just had to wait until I actually had the part designed in order to print it. This final module is the NanoRacks Bishop Airlock, which is mounted to the station's starboard side of the Tranquility Node 3 module. Since I had previously installed a threaded rod here along with the CBM adapter, I had to remove the threaded rod and then glue the CBM adapter in place with an outwards facing magnet. Unlike most other airlocks on the space station, this one is not used for spacewalking, and instead is used as a means of passing experiments from the interior of the station to the exterior. The JEM module airlock as well as the experiment airlock on the Russian side of the station were used for similar purposes. However, Bishop provides a much larger volume for stations that need to be sent outside the station. Once something has been placed inside the airlock, the hatch is closed and the robotic arm will lift the airlock off of the CBM, allowing the experiment inside to either deactivate or deploy. Once this is done, the arm will then relocate the Bishop airlock to the CBM it was previously located on. This process can also be used to deliver tools and equipment to spacewalking astronauts, and also to deploy satellites. The airlock itself was primarily manufactured by NanoRacks, with some components also built by Boeing and Tele in Italy. The version that I made here is a single part that is printed in multicolor, and I used a magnetic means of attaching to the CBM to allow the airlock to be easily removed and reattached to the model space station. Unfortunately, I didn't get much video of me actually doing this while I was first building the model. Next up, we'll be working on installing external payloads to the station. These are primarily mounted on the zenith and nadir sides of the truss, so you're probably going to want to rotate the station around such that the forward of the station is closest to you. This is also a good time to add magnets to the pressurized mating adapters if you haven't done so already. Again, make sure that if you already have any visiting vehicles here, your magnets are properly aligned such that they are actually able to dock. Of the 8 external platform elements on the station, 4 of them are Express Logistics Carriers, or ELCs, 3 of them are External Stowage Platforms, or ESPs, and the last is the Alpha Magnetic Spectrometer, or AMS. We'll start by building the ELCs, and I'll note here that since all 4 of them are very similar in design, I'll only show the construction of just one. The ELCs are external platforms for scientific experiments to be mounted on the exterior of the station. In this regard, it is similar to the Kibo module's exposed facility. This is essentially the unpressurized version of the ISPR racks inside the station, also known as Express Racks, which stands for Expedite the Processing of Experiments to Space Station. Okay. In addition to housing experiments, they can also hold spare parts for the station so that they don't need to be flown up on a new mission. These spare parts are known as Orbital Replacement Units, or ORUs. Since the hardware that is mounted to these platforms is occasionally swapped out for other equipment, the accuracy of these models may be subject to change. Now I'm going to break up this external payload section just a bit because the sequence in which you install these external payloads can be optimized if you do them in a certain order. So with that, ELC 2 and 3 both mount to the Zenith side of the station as well as the AMS. So let's start by installing those 2 ELCs first. The ELCs mount to the far ends of the port and starboard section 3 trusses on both the Zenith and Nadir sides. Now when you actually go to glue these in place, there isn't a whole lot of surface area for them to contact the truss itself, and while I did find that the glue was sufficient to hold them in place once it fully dried, you might want to also try this tape method that I used to actually get them to sit on top of the truss in the first place, just to be safe and make sure they still balance. Now I will note here that at least in the manual I used, there is a typo in the specification of which ELC is which between ELC 2 and 3. Both of them were labeled as ELC 2 for me, but the actual design of each element and its placement on the station are correct. And if there's any uncertainty, you can always refer to the NASA documentation as well. There's not really a direct indicator of the exact lateral placement of these elements, so I tried to match it up as closely as I could with the manual. While we're still working on the Zenith side of the truss, we can also go ahead and construct the Alpha Magnetic Spectrometer. This is a high-precision astrophysical research element that catalogs incoming cosmic rays to detect antimatter and potential signs of dark matter. Now, the operations and theory behind this machine are way beyond the scope of this video, but at the very least, we can say that it is a high-precision and high-power requirement experiment that wouldn't have really been able to have been deployed into space if it hadn't been for such a large infrastructure as the International Space Station being available. Development of the module was a major international effort, but final testing and integration operations were completed by CERN in Switzerland as well as ESA. After all this, the AMS was flown up to the space station on the second-to-last space shuttle flight. In a similar manner to the ELCs, the AMS can be installed on the starboard Zenith side, just on the port side of ELC 3. In order to attach it at the angle that you see in the actual space station, I would recommend using the tape approach that I have demonstrated previously. As long as you can get enough glue between the element and the truss itself, it should hold even at the slight angle that it has. You can also use an additional piece of tape to sort of pull it into the angle if it's not sitting properly when you just use the 2 pieces of tape on the side. At this point, we can construct the final fixed external elements, these being the external stowage platforms. These are primarily intended to house additional ORUs for other parts of the space station. And so where the ELCs are primarily intended for experiment operations, the ESPs are more like storage shelves. ESP1, which mounts to the port side of the Destiny module, is unique in its design, but ESPs 2 and 3 are based off of the Space Shuttle Integrated Cargo Carrier, which was essentially an adapter plate for housing payloads within the Space Shuttle cargo bay. Now unfortunately I didn't get a video of me building ESP1, but since it's only comprised of 3 components, you can probably figure it out from the manual. And so to go about installing the ESPs, we can first install ESP1, which as mentioned attaches to the port side of the Destiny module. This one's kind of tricky to line up exactly, but approximately it should be mounted such that the 2 boxes are approximately evenly spaced about the front face of the truss. If you're using a clamp setup like I have shown here, you're probably also going to want to do this installation while the station is being held by the clamp to make sure that you can actually grab it again in the future once the station has been removed from the clamps. Now to install ESP2, it's probably easiest to just remove the Quest airlock from the station completely. The ESP mounts to the 2 trunnion mount points that are located on the same side of the module as the EVA toolbox, which is this small part on the smaller cylindrical section that looks like some boxes. If you have already attached the trunnion pieces to these mount points, It may be difficult to remove them if you've already used a lot of glue to get them on there in the first place. But at that point, if you're having difficulty, you can always just remove the pins from the trunnions and just glue the ESP to the platforms of the trunnions themselves. You may also want to use the taping approach that I mentioned earlier to hold the ESP in place while the glue is drying, since it's not very well supported on its own until this is done. Now, I did not get a video of me reinstalling the airlock to the station, but I was able to do so successfully without disassembling any more of the station. Also keep in mind that with the ESP installed, it should be facing the station forward side of the airlock once the airlock is reinstalled to the station. Now, to install ELCs 4 and 1 and ESP3 on the nadir side of the station, you're probably going to need to flip the station upside down. Now, this was fairly doable with the same clamping approach that I was using earlier, but it's important to recognize that the orientation of the station is reversed in this configuration. So if you're standing at where I was in the video and you're looking at the forward side of the space station, the port side will be on your left and the starboard side will be on your right. The reason I'm driving this point home so hard is because I did install these backwards in the first place because I was looking at the manual assuming that the station was still upright. So keeping this reorientation in mind, ELC1 installs to station port side, which is the left-hand side of the station when you're looking at it in this configuration. ESP3 installs to the starboard side of the station on the far end of the S3 truss, which is the right-hand side of the station when you're looking at it the way I have it here. ELC4 also installs to the starboard side, but it mounts to the port side of ESP3 on the starboard truss. And of course, if I am making this more confusing than it needs to be, you can always refer to the NASA documentation or the manual. As we approach the final space station components, we can now construct some of the elements of the mobile servicing system. This includes the space station remote manipulator system, otherwise known as Canadarm2, and the mobile base system, which slides along the two rails that we installed for additional support on the truss. This system also includes the special purpose dexterous manipulator, also known as Dexter, which is another robotic system on the station that was not included as part of this model, and understandably so, as it is quite complex. I'll start with the MBS to get that out of the way before we get into the robotic arms. The Mobile Remote Servicer Base System, or just the Mobile Base System for short, is a sort of trolley that slides along the mobile transporter railway that runs the length of the primary truss structure. While the arm on its own is capable of relocating itself across the space station, as we'll see in a moment, the MBS allows it to be positioned with much greater accuracy, and also allows the arm to be carrying something as it moves across the station. Both Dexter and the Canadarm are able to use the MBS to traverse the truss. Now, while actually constructing the truss elements of the MBS in the 3D printed model isn't terribly difficult, it's also a bit finicky to get the chamfered truss parts to attach properly. For me, though, the greater challenge was trying to attach the magnets to both the grapple fixture sites as well as on the bottom platform that will slide along the two rails. Now, the grapple fixture magnets themselves aren't terribly difficult to mount, although it is important to make sure that you get them all lined up the same way so that the arm can attach to any one of them. The base magnets are a bit trickier though, as since they will need to be mounted pretty close together, it can be a bit tricky to hold them in place without them attaching to each other in the process. This could perhaps be improved by having a metal work surface that the magnets can stick to while they're being glued in place, but I didn't try that myself, so your results may vary. Technically, you probably also don't need to have all the magnets aligned with the same polarity on the base of the mobile base station, but it seemed a little bit easier to actually assemble in this manner. Also, depending on the exact spacing of the truss support rods, the magnets themselves may not properly attach to both rods at the same time when the MBS actually gets installed. This wasn't a huge deal for me though, as long as the zenith magnets attach to the zenith rod, it's still able to slide along just nicely. Next up is the first of the two robotic arms included as part of this model, the Space Station Remote Manipulator System, or Canadarm2. Now, the original 3D printed version of this arm does not include any sort of magnets to allow the arm to be positioned or relocated. But of course, I had to go and overcomplicate things, so I decided to add some small magnets to the joints of the arm. This can be done by printing off the two halves of the segment of the arm that does not include the pin joint. You also may have to remount the socket joints with a small drill bit to get the magnets to fit. In each joint segment, I found it easiest to actually get the magnets to fit in place and to potentially add some additional strength if you apply glue to the socket first and then fit a pair of magnets into the socket. This way you can mark one side of one of the magnets and slide it off of the other after the glue has dried. If the second magnet becomes attached by the glue, then this just gives you additional strength to the magnetic joint. When gluing magnets to the latching end effectors, you can first attach the magnets to the arm joints that will be attaching to the LEEs, and then apply glue to the surface of the LEE where the magnets will attach before taping the part in place. This assembly process is pretty tricky to do without getting glue on your fingers, but it's also quite a bit easier than the JEM remote manipulator system. Now, as you can probably tell from the name, this is a Canadian component that was built for the space station by the Canadian company MDA. And in fact, this is the same company responsible for the original line of Canadarm series, which were built to fly aboard space shuttles, as well as the Mobile Base Station and Dexter. They are also working on a third iteration of the arm for the Lunar Gateway space station. The Canadarm on board the station is a pretty complex robot despite only having a few different segments. Each end of the arm has a latching end effector that can grab onto various grapple fixtures across the station, as well as any visiting vehicles that are equipped with an appropriate grapple fixture. The 7 joints in the arm itself allow it numerous degrees of freedom and the ability to inchworm across the station by attaching to various power and data grapple fixtures that are located in strategic locations. At each of these PDGFs as well, the arm can be controlled from either the Cupola or another control station in the Destiny laboratory, or alternatively by NASA Mission Control or by CSA's Chapman Space Center. The arm is capable of carrying both payloads across the station, as well as astronauts, allowing them to ride on the end of the arm to improve access to difficult-to-reach parts of the station. Now, when attaching magnets to the grapple face of the latching end effectors, it's important to make sure that the polarity of these magnets lines up with those on the mobile base station. If you don't have a compass available, like me when I was building this, you can just attach 2 magnets together and then mark one side to indicate which one is which. Once you do this, you can glue the appropriate side to the arm such that the magnets will attach to the MBS. It's also worth noting here that even with the addition of these magnetic joints, the arm still doesn't have all the degrees of freedom that it does on the actual space station. But since the magnets at the elbow joint are not rigidly attached, you also get some additional range of motion with the magnetic joint, as the magnets can still hold on to each other when they're not face to face. Now, as mentioned previously, when you go to install the MBS onto the truss rail system, depending on the spacing of the truss rods, you might not be able to get the magnets to attach to both of them at the same time, or at least they might not both attach to the same face of the magnets. Now, even though this happened to me, I was still able to slide the MBS along the truss just fine. If you really want to go crazy with this model, you could also add in some additional magnets to represent the PDGFs that are located across the station to allow the arm to inchworm across the model. I was fine with just using the MBS to move the arm across the station, but if you do this, please let me know in the comments because I would be very interested to see that. So now that we have effectively completed our space station model, I'm also going to include here the visiting vehicles that I used as part of this assembly process, in case you want to add these additional elements to the model, or if you just want to learn a bit more about station operations and history. Now, the first point to make in regards to visiting vehicles is that there's one more modification we can make to the station if you want to enable the ability to support berthing visiting vehicles to the nadir ports of the Node 1 and Node 2 modules. And that is to replace the CBM covers that we used previously on these modules with a modified version with a cutout that's big enough to hold a larger magnet. This will allow you to berth visiting vehicles such as the Cygnus and HTV vehicles, among others, to these modules. Doing this for both Node 1 and 2 will also allow you to have multiple visiting vehicles berthed simultaneously. I'll also mention briefly here that the Cygnus cargo vehicle is a primary means of resupply for the International Space Station. It was originally developed by Orbital Sciences Corporation, which over the years eventually became part of Northrop Grumman. Its construction is also supported by Thales Alenia in Italy. The Cygnus vehicle uses the common berthing mechanism to berth to nodes 1 and 2, which gives it a bigger cross-sectional area for cargo transfer than the standard docking adapter. The 3D printed version I have here is also an enhanced Cygnus, which has additional space for cargo and is slightly longer than the original design. I'll also note here that if you do want to print a full color version of the Cygnus like I did, be aware that with the default bamboo print settings, you're going to waste quite a lot of material getting this thing made. Next, we can jump back in time to the Soviet spaceship that is still used to this day. The Soyuz series of spacecraft is one of the most refined vehicles in human spaceflight. The first iteration was launched in 1966, and over the decades it has been upgraded numerous times and is still used for ISS transport today. In fact, another Soyuz mission was launched while I was recording this video, that being Soyuz MS-27 on April 8th, 2025. The vehicle consists of 3 segments: an orbital module used for living space and cargo capacity, a descent module which is occupied by the crew during launch and re-entry, and a service module containing support systems for the spacecraft operation. Perhaps one of the most important design elements of the orbital module is that it contains a space toilet. Only the descent module actually returns to Earth, as the other two modules are jettisoned before re-entry. With its extensive legacy of spaceflight, this is also one of the safest space vehicles in current operation. A Soyuz craft can support a crew of up to 3 people, with life support capabilities to support crew for much longer than the 2 days it usually takes to get to the station. However, as long as the vehicle is docked to the ISS, it can be operated for up to about 6 months. The exact version of the Soyuz I'm using here is a Soyuz T model, which was only in service from 1979 to 1986 and was used to dock to the Salyut 7 space station. The design has changed slightly since then, but this still is similar enough to get the point across. The next visiting vehicle we'll look at is the Progress spacecraft. This originally Soviet vehicle is based heavily on the Soyuz vehicle, but with modifications to support its intended operation of cargo delivery. In particular, the re-entry section of the module is replaced with a tanker section that houses additional propellant. This allows the Progress to be used to resupply the International Space Station's propellant supplies, and also to boost the station to keep it in orbit or to change its orbital trajectory. Like the Cygnus, the Progress vehicle is also not designed to return to Earth and simply burns up in the atmosphere as it re-enters. I'll note here that this 3D printed model is primarily based on the Progress M version of the vehicle, but shares the cursed docking strut with the Progress 7KTG version, which was the first version of the Progress to fly. Now, for an added point of realism when you go to dock these Soviet spacecraft with the International Space Station, there is actually a distinction in which docking ports on the Russian orbital segment are used for which spacecraft. Technically, the docking adapter is compatible between both versions, but there is some operational constraints that generally limits the spacecraft that dock to each module to a specific version. The Soyuz usually docks to either the Rassvet or the Prichal node, while Progress will dock to the Zvezda aft or the Poisk airlock. The primary reason for this distinction is due to the leak in the Zvezda module. In order to keep this leak under control, the hatch at the aft of Zvezda is kept closed whenever possible, so keeping it open for a visiting crew would increase the leak rate. Progress also docks to the Poisk airlock because when the airlock is cycling, it blocks access to the visiting vehicle, and in the event of an emergency, the crew needs to be able to access a docked Soyuz vehicle in case it needs to be used as an escape pod. The last visiting vehicle we'll look at here, and the last component of the space station model, is the SpaceX Crew Dragon. This was the first vehicle developed entirely by a private company to dock with the International Space Station. And with the first crew launch of Dragon to the space station in 2020, this also ended NASA's reliance on the Soyuz vehicle to launch astronauts to the station, since after the retirement of the space shuttle, this was the only way to get up there. I made some modifications to this 3D printed model to allow some more realistic operation of the hatch and docking adapter. Part of this was a modification of the docking ring to allow a magnet to be inserted, as well as a cutout in the main body for a replaceable hinge component that could allow the hatch to actuate. This was really tricky to get actually working with this small scale, and so far I've only been able to get the hinge to actuate several times before the hinge fails. At least with this existing design though, I was able to hold the hatch in an open position and attached a magnet to the inside of the hatch as well to make sure that it can actually stay attached to the Dragon when it's configured with its accompanying launch vehicle. In its nominal configuration, the Dragon can carry up to 4 crew members, but can be reconfigured to support up to 7. Additional reconfigurations can also be made to allow for spacewalking, by replacing the international docking adapter with an airlock. The primary structure of the Dragon consists of an orbital module and a cargo module known as the trunk. The trunk is expendable, but the orbital module is entirely reusable, by deploying parachutes after its re-entry and then landing in the ocean. Of the 17 missions that have launched so far, they have all been carried out by one of 4 vehicles, with a 5th vehicle having a planned launch in 2025. The vehicle has life support capabilities for up to 20 person days, or 5 days with a 4-person crew, and like the Soyuz, does include a space toilet. Also, when I went to actually 3D print one of these, I had a lot of trouble using Bamboo Studio to apply the multicolor settings to the model, and since I had most of the rest of the station put together at this point, I just decided to use Sharpies at this point. But I think it still looks alright from a distance at least. The Dragon model that I used also includes the trunk cargo section, but since it prints in one piece, I didn't include it with this assembly video. And so we have completed building and assembling our model of the International Space Station. As you can probably tell at this point, the completed model is quite large, and so finding a place to put this thing might be a bit of an additional challenge. But especially with the application of some directed lighting, I think it's pretty well worth it. Overall, this whole project was a lot of fun, and I got to go into a lot of detail with researching the station, and so it was an excellent learning opportunity. It's also one of the largest 3D printed assemblies that I've ever put together, and so it was good to get some experience in that regard as well. Once again, if you haven't already, definitely check out the original authors of all these 3D printed models, as they did an excellent job converting the actual space vehicles into 3D printable versions. As a concluding thought to this project, I'll mention that as of time of recording, there are only 2 space stations in orbit around the Earth. However, there are a fair number of additional space stations that are currently in development, and within the next couple decades, it looks like there could be several space stations in the vicinity of the Earth and Moon. And so this project really made me think a lot about the name the International Space Station. As of now, this is the only one of its kind, but it sounds like a pretty cool future when the name International Space Station isn't specific enough to determine which space station you're talking about, which makes me even more excited to be working in the space industry at this point in history. And so on that hopeful note, I'll close out this video by saying thank you very much for watching. As you may or may not be aware, this is a bit different from the usual stuff that I do in this channel, but as you can probably imagine, in addition to reviewing science fiction, I do occasionally enjoy working on engineering projects now and then. And so if you'd like to see more projects like this, you can feel free to subscribe to be notified next time I have one ready to go. And if the idea of a space engineer reviewing sci-fi video games sounds interesting, you can also check out some of my videos of that as well. And so with that, I hope you enjoyed this video, and thank you very much for watching.